Hello everyone, Atheatos here. And yeah, the time has come. The time to hack a 486SXLC2 into this little 386SX lab rat. You see, this motherboard comes in with a soldered 386SX CPU, and I have seen variations of this board with a Cyrix 486SLC. So in general, Cyrix processors are supported, but for sure there's no prediction here for a 486SXLC2. And that is what I will try to do today with this custom adapter. The adapter not only handles the signals, but also has a voltage regulator here on the back to generate the 3.3 volts that are needed for the V-core. So the plan for today is to remove this CPU. Of course, this will not be wasted. I will move it to another adapter that I will slightly adjust for the 386SX. Then, of course, I will open all these holes and solder some female pin header. These are not your standard 100mm pin headers. These are the smaller 2mm ones. So yeah, you get the idea. In the end, I will have here the pin headers, and I will be able to easily swap between the 386SX and yeah, the 486SXLC. Now, removing the chip here is not that hard. I will use the classic rose metal technique. I have done this before when I removed my soldered 386DX and installed the socket there. You can check this video up here. The hardest part will be to open all these holes, but I will manage somehow. I will also open these holes here for the floating point unit, and then install just a socket here. Now all this is a lot of work, and yeah, I'm gonna do it off camera. Yeah, it's just not that comfortable to do this fine work under the camera, and I want to be as careful as possible. Also, of course, okay, I made these adapters. This in the end is a hack, and of course I'm not 100% sure if this will work today, but okay, we will see. So now, before I proceed and do all this stuff, let's have a look on all these 486 chips for 386 systems from Cyrix. I have demonstrated before in my channel this the 486 DLC. That is the most basic model. You can check my previous video on that. So this is a 486 core with 1 KB of level 1 cache that fits the 386 socket. And okay, it is the 32-bit bus version, but actually there is also this, the 486SLC. This is exactly the same, it is just the 16-bit variant. So yeah, this one is the one that is soldered on many motherboards that look like the one I have here. Then there are a few other variants. Yeah, okay, these are all the SLCs. The only difference here is different frequency and voltage. And then here is the interesting stuff, the 486SXLC that we also have here. This chip upgrades the level 1 cache from 1 KB to 8. And then of course the SXLC2 also features an internal clock doubler. So okay, you can have the bus at 30 MHz and the internal frequency at 60. This clock doubler is not fixed, you can enable or disable it with some configuration bits. Finally, okay, just I have to mention that there is also a 486SRX2. This is just an SLC with clock doubler. So yeah, the cache is 1 KB, but you have this clock doubling here. In other words, looking at all this, the chip I have here, the 486SXLC2, is the top of the line. Now, if I want to be completely fair here, there is also this 486SLC from IBM, and here things are getting a bit confusing. This chip has nothing to do with the Cyrix chips. They licensed the 486 from Intel, but in essence these chips are very similar to the 486SXLC from Cyrix. These also have variants with clock doubling and tripling of the clock. The top model even manages to run at 100 MHz, 3x33. Now these chips are not easy to find, and I have not seen any dataset of them, so technically these are the top chips, but in the end this is definitely a story for another day. So let's now have a look at the datasets and the pinouts here. And I will start with a basic Intel SX1. This really is the base, and all the signals here are mandatory for operation. We can see there are a lot of pins that are not connected, like pin 20, the 3 pins here 29 to 31, and also a lot of pins here 43 to 47. So the connectivity here is the same as on this motherboard. Then other CPUs like the one from AMD here has exactly the same pinout, and the only difference is here that it takes use of some of these not connected pins to add some additional functionality. I can see easily these 3 here and the 43. These extra functions are actually optional, so my motherboard still has all these unconnected and it's not a problem. Then if we see a 486SLC, here we have a lot more of these not connected pins used. We have these 3 and 4 more here. And pin 30 is this legendary flash signal that is used for the coherency of the internal cache. And finally here is the pinout of the 486SXLC. Here also the 20 pin is used. These 3 are used and are exactly the same as the 486SLC. But here these are actually different. Either way, most of these are unconnected on the motherboard, so I don't really care. These are optional features for power saving or something like that. But one important pin is this one, the VCC 5 on pin 45. And now I have to turn to another page of this datasheet. You see there are many different chips of this 486SXL. SXL is the full 32-bit, okay, SXLC is the 16-bit. If after the main model you have a dash and a number, then this is a 5V chip. So a chip like that you can solder it directly on the motherboard. Okay, good luck finding something like that. Then there are chips with a V. So V25 means 25 MHz and 3.3V. And finally there are the G, like G50. And this is the chip I also have here, that have a dual voltage, so the core is 3.3V and the I/O is 5V. So when you have a chip like that, all the VSSA here should be connected to 3.3V, and then the VSSA 5, it is the 5V for the I/O. All the other chips have this 45 pin as unconnected. So yeah, this is important because if you don't connect this, the CPU will never work. And if I am to connect another chip here, like the 486SLC, I have to be careful because this is used for another function. So these are more or less my notes. So finally, one thing I want to note about this motherboard is this little note on the top side. It says OP1, open 386SX, close Cyrix. And this OP1 thing is quite strange because I mean all the jobbers are GP something and there's nothing OP on top of the motherboard. But if we look here, close to the CPU, there is this OP1 and it looks like 2 pads that are not connected. And if we trace this, it goes to the socket of the CPU, and this pin is the pin 30. And as we checked into the manual, the pin 30 is the flash pin, so that means that this motherboard properly supports the flash function, and you just have to connect this here. This is by default unconnected, because on the same pin the AMD 386SX has a different function. So yeah, with Cyrix CPUs you have to sort this. Now of course this is a very interesting topic, and if this CPU works, I'm gonna test with or without the flash, both in software and with this sorted or not. Yeah, very interesting stuff. So time for a small pause, and let's hope for the best. So here we are, everything is done now. And there are lots of good news and okay, some bad ones. The most important thing of course is that everything worked on the first try. So nothing popped, nothing burned out, and that is always a good thing. The results, as we will see, are a mixed bag. But first of all, let's have a look at the hardware starting from the motherboard. And okay, look how nice this looks. We have here the pin headers for the CPU, the socket for the floating point units, the any-clock device, and okay, I also added a few high quality capacitors here. Overall this looks very nice, right? Then on the back side, here I connected the OP1 for the flash signal, and I also added these 2 pull-up resistors. Now these are a bit bulky, but I have ordered some smaller ones to replace them in the future. Now regarding these 2 resistors, okay, checking the manual of any 386SX CPU, from the first one from Intel to the 486SLC1, it's a clear recommendation here to have a pull-up on the ADS and lock pin, and I couldn't measure anything on this motherboard, so I added those 2 resistors. In the end I didn't notice any difference. I don't know if the chipset handles this either way. However, as I said, it's a recommendation in every manual, and in the end a 20k resistor cannot make any harm. So then of course we come to the CPU modules, and I made two of these with the 486SXLC, and here you can see it with the pins and all. Yeah, I know, these look very cute also. And finally, of course, I transplanted the old CPU to another module, and here we have these two. And the interesting thing is that I modified the adapter here to fit the 486SX. Okay, first of all, there's no voltage regulator here, and the 5 volts goes directly to the voltage of the CPU. And secondly, I removed the VDD-IO here, the 5 volts, and the flash signal. So while the flash signal is permanently attached on the motherboard, it will not drive the pin of the CPU, as is cutted here on the adapter. All that means that I can just swap CPUs here between the 386SX or the 486SXLC without changing any jabber or any other configuration. Also, these pin headers are actually quite nice. You can place a CPU without a lot of force and then remove it quite easily. And it is a nice fit overall. So this is the final result. And yeah, this looks beautiful, right? Absolutely beautiful. So all this is nice and well, but what about results? And first of all, let's talk about the 386SX. I mean, there is a question here about the ability to overclock now that we transplanted into this little adapter. And first of all, nothing changed. This is still completely stable at 43.7 MHz. But then I figured that though the system does not post at around 45 MHz, if I start my system with a setting here that is below that, and then hot plug a jumper that increases the frequency, I can even run this now at 50 MHz, and this goes completely stable, and I could run benchmarks just fine. Posting of course is impossible at 50, but yeah, with this hot plug method, and maybe in a strange way, the system goes completely stable at 50 MHz. Now of course I don't want to get too much off topic, but okay, for sure I have to show you some proof, right? So of course during booting the CPU clock is reported at a lower frequency, as this was the frequency that is used during post. However, after changing the jumper and going into the benchmarks, here in the system information it is reported correctly the 50 MHz, and this is the score. So this is now above 486DX at 33 MHz. And here is landmark, again 50 MHz and a very nice score. This is the cast check tool, 386 at 50 MHz. And this is checkit with a very high score of 8.84. Then 3D bench with 13.9 and PC player benchmark with 3.1. Now Doom minimum details, and this is 3260 realtics or 22.9 frames per second. Very nice. Now high resolution, this is 14600, that is 5.1 frames per second. Okay, that's not that bad for a 386SX, but still way below the results I got from my 386DX at 40 MHz. So that is our little parenthesis here about the 386SX. And the question remains, what about the 486SXLC? And first of all, as I said, these two worked both in the first try, and they ran fine at 40 MHz without clock doubling. I tried to raise the frequency, but yeah, these are only stable around 40 to 43 MHz, and it didn't matter if I hot plug here or something or not. Now for the story, I also have full access to the voltage regulator of the CPU. I have set it by default at 3.3 volts, but of course I tried also higher voltages. Yeah, okay, something like 3.9 volts, but this also didn't help with the overclock. In the end, it is a limitation of the CPU probably, or I don't know, the motherboard in combination with it. So yeah, 43 is the maximum. So then there was another interesting problem here. You see the system was not posting with frequencies below 30 MHz. So in the end, all this setup was only useful between about 30 to 40 MHz. Then I did lots of tests, and yeah, the problem was with the BIOS. So again, I tested various different files here, and yeah, I finally returned to the original BIOS. this was able to boot the system at any frequency. Of course, okay, the maximum one was around 42, 43, but yeah, that is a limitation with these chips here. Now the original BIOS is missing a few settings, and most importantly the slow refresh rate for the RAM. However, either way I used the AMI setup tool and set these options, and the performance was the same in the end. Now, okay, let's talk about the elephant in the room, the clock doubling function here. And this is where the pain begins. You see, when I tried to enable this function using the Cyrix -cd command, the system just froze here. Then again I tried many different things as different tools to enable this. And yeah, this line here is from another tool, but also doing it with this one, the system froze the same way. I also tried with some assembly commands and a little COM program, again same result. Then I tried again different BIOSes and even the award one, and yeah, with award you can hard mode the register configurations for the Cyrix CPU. Yeah, changing the bits there to force clock doubling from the boot resulted in a system that just does not post. So first of all, we can conclude the problem is not with the tools, the problem is with the function itself, and okay, when you set the bit, the system freezes. And then I witnessed a bit of different behavior when I run here the system at 25 MHz. Yeah, it looks like that the chip somehow tests to see if the bus speed is near the nominal frequency, that in this case is 25. So in this case, when I run the same command, I got something like this. Yeah, this is definitely a different behavior and only happens when the bus is around 25. This looks like a broken menu of our BIOS, but in the end, okay, you can do nothing here. You cannot return to the command prompt or something, and the system is broken. So no clock doubling for us. Another thing I tried was with less memory, and in this case we don't get this glitch, the system just restarts. Then, because I was worried a bit about the any clock mode and that maybe this is interfering with all this clock doubling process, I removed here the crystal and just had the any clock device to get the reference clock as an input. So in this case, this device is more or less working in a very similar way as the one it replaced, and the generated frequency is just a multiple of the reference one. But again, no success, and the behavior was the same. So freeze when the frequency is not close to 25, and all this strange stuff, or reset when it is close to it. So the clock device, again, it's not a problem. I also tried some pull-up resistors and stuff like that in the clock network, also to just see if there is any improvement in overclock, but no change there. So in the end, it looks like that on this motherboard, on this setup, yeah, probably enabling the clock doubling is impossible. And the reason for all that, I don't know. It might be a bug or incompatibility with this chipset here, or the BIOS. It can be a missing routing here of some of these signals. And okay, all this is very hard to debug and find. So yeah, I don't know, I might come back to this in the future if I find something. And of course, if you ever witnessed behavior like that and you have any suggestions, please write below. I will try them immediately. But as for right now, okay, I have spent a lot of time on this and I cannot do much more. Then okay, the clock doubling is not working, but what about the other settings? Yeah, with the registers and the Cyrix tool. And the situation looks very similar to what I witnessed with my 386DX motherboard and the 486DLC. Yeah, of course, first of all, you need to have the cache enabled by the BIOS or this CR register. This first 64K of its 1MB boundary set as cacheable gives a small boost. Now in this case, I just put this region here as not cacheable and I didn't bother with the special not cacheable regions. It's more or less the same. The A20 input is enabled and connected in the motherboard, so everything is good here. The flash or barb input is again something very strange and annoying. I had to do a ton of experiments. This enabled or the other enabled or both enabled or both disabled, with or without the flash pin connected. And in the end there was no difference whatsoever. Yeah, that was very disappointing and annoying, so I don't have something special to show you. And really the only difference here regarding the flash topic is that when you have the signal unconnected in the motherboard, the speedsys was looking totally destroyed, full of artifacts and freezed. But as I said, everything else was working just fine and performing exactly the same. This internal cache mode, it is the flag for the clock doubling that is not working. And this sup A on my 386TX froze the system. Here does nothing, because here the signals are properly unconnected. So that's more or less, and then of course I skipped on purpose the CAN input. So now this is very interesting and I made a great discovery. So this flag here enables the CAN input of the CPU. This is an input that tells the CPU to use the cache or not. So in other words, if you have this enabled, you can disable the cache using a jumper or something. Also, this CAN pin is activated when pulled down, and there is an internal pull up. So if you just enable here this input, your performance will suffer as the cache is disabled. And that is true for all these Cyrix CPUs. The performance is actually lower than even totally disabling the cache here. And then I had the idea, okay, let's keep this enabled and just pull this pin high. So this is what I did here on my second adapter. And yeah, this is just a resistor here to pull the CAN pin high. And yeah, in the end, there was an increase in performance here. So it's better to have this CAN enabled and pulled up. The increase of course was not much, but it was there. And most importantly, it was Doom that gained something for 5% more. So in the end, all my benchmarks were done this way. So regarding benchmarks, as I didn't go that far with overclocking here, I see no point presenting to you my 42 MHz results. I mean, okay, this is something like 5% faster than the 40 MHz, but in the end the 40 are more useful for comparisons. Then of course I tested with or without the cache enabled, and we are gonna see all this compared in a table later on this video. So as for right now, I have for you the results at 40 MHz with the cache enabled. So first of all, here is check it. Yeah, around 50.7 times the IBM XT. Video performance and hard disk performance, that is okay, more or less the same as the 386SX at a bit more than 2 megabytes per second. Then VGA speed at 42.2, quite high. And yeah, here the vid speed. Then system information, okay, Cyrix 486, 40 MHz. And this result here that puts the system close to the 486DX at 33 MHz. Then here is landmark. Yeah, this is a very high score both for the CPU and the video speed. Cache check tool. And okay, I don't know how interesting is all this for you, but I think it's important to give all this information for reference and comparisons, and also for me to have them in the future. The cache is all enabled and well, 8 kilobytes. And yeah, the speed is about 60% faster. Okay, you might think that this is not much. However, keep in mind that this CPU is heavily bus limited. Yeah, really the bottleneck here is the bus. So having this cache here means that the CPU just doesn't have to access the memory that often. And that will make a great difference, as we will see. And here is speedsys. And yeah, the score here is very, very high at 20.3. And here we can see again the 8 kilobytes of L1 cache is enabled, and this cache is something like 50% faster than the main memory. Then finally some 3D bands, and the score is 21.1, very nice. Then PC player benchmark, and this is 5.7. Then Doom minimum details, and this is 1960 Realtix, or 38.1 frames per second. Yeah, this is a very good result, and overall it's clear that on same frequency at 40 MHz, the CPU is nearly 2 times faster than the 386SX. And of course the picture is here the same at full details, with 7120. This is actually 10.5 frames per second. Now okay, the one might be too small, the other might be a bit unplayable at 10 frames per second. But if we go to something more normal here, we can see that this looks quite nice actually. And yeah, here I got this, that is 21.4 frames per second. Not the best, but yeah, I think it's playable. So here we are with all the results from the tests I did. and we can draw a lot of interesting conclusions here. So first of all, on the top I have some old results from my 386DX system, and then here are the new ones, the 386SX at 40 MHz, at 50 MHz, the 486SXLC at 40 MHz with the CAS disabled and then again with the CAS enabled. So everything is here, 3D bands, PC player benchmark, Doom min details and max details, VGA speed, sysinfo, speed sys, and check it integer. So the first thing to note here maybe is the comparison between 40 and 50 MHz 386SX, and the difference here is more or less what it was expected, around 20%. Well, actually it might be a little bit higher, and I'm not 100% sure why. Well, what is happening here maybe relates to the bus bottleneck. You see the bus has to handle both all the memory traffic and the ISA bus traffic, and with 50 MHz it just has more room to move. Still, yeah, this is a bit strange. Then the most interesting thing here and the most ridiculous one is the performance of the 486SXLC with the CAS disabled. And if we compare it with the 386SX at 40 MHz, yeah, the 386SX wins. Yeah, okay, if we be a bit more careful and we check only the important benchmarks, these two are more or less the same. In some, the one wins or the other, and this again highlights how much the bus is a bottleneck here and nothing else matters. So the 486 core here has no effect in performance, and in contrast to that I have to remind you that the similar comparison back then between the 386DX and the 486 DLC had the 486 DLC win by more than 18%. So here the bus bottleneck just destroys all these benefits. Then when the CAS is enabled, it's a day and night case. All numbers are here nearly doubled, maybe more actually. Yeah, look at these ridiculous Doom scores here. This is something like 2.5 times up. Absolutely ridiculous. So yeah, in total, I don't know, this is more than 100% boost. While on our 386DX system, we had a total of 37%, with the contribution of the CAS being only 15%. Of course, there the integrated L1 CAS was only 1 kilobyte and here is 8. But the most significant factor is of course the bus bottleneck, where the CAS of course helps a lot. So if we compare this at 40 MHz with the integrated CAS to my previous DX measurements, yeah, this setup is actually quite close to an AMD 386DX at 55 MHz or the 486 DLC at 40 MHz. Keep in mind here my old measurements were with a floating point unit, and this helps the PC player benchmark results. So the SXLC loses in 3D bands, sits between the two systems in PC player benchmark and in Doom, and of course it loses in VGA speed, but this again is because the ISA bus here is overclocked. Finally in Checkit actually beats both of them. So yeah, in the end it's very comparable. Now, as a final comparison, I have here again the results from K2's Retro Workshop. I will link again his video in the description. So what he had there, he had a 486 SLC. This is a 1 kilobyte CAS chip, overclocked at 50 MHz with a very fast ISA VGA card, the ISA bus at 20 MHz, and an ALI motherboard. So yeah, in general, this motherboard is way better than the very cheap one that I have here. So compared to my setup, okay, I'm losing 21% in 3D bands, 10% in PC player benchmark, and okay, if we combine these two, around 5% in Doom. For sure I'm losing the most here in 3D bands, and the reason is of course because here we have high frame rates and the effect of an overclocked ISA bus is significant. My system runs the ISA bus at the default frequency of 7 MHz. Then our difference is the smallest in Doom, and yeah, maybe the reason also here is this Ken pin optimization I did that also gave me 4% more. So yeah, in the end the 8 kilobytes of CAS definitely helped here, but these are not enough to beat a highly overclocked 486 SLC machine. By the way, I'm also waiting for some 486 SLC chips, and I will test them also. Maybe I will manage also 50 MHz, we will see. So here we are, we managed to get a ridiculous speed up here of 100% with this mode and the 486SXLC. Unfortunately, I'm still not happy here. I was hoping for something way more, but the clock doubler never worked. And this is quite uncomfortable, as on the one hand we had this significant improvement, but on the other hand this CPU is underutilized here. Either way, I like this little system and how it looks, and I also now have these little CPU modules that I might find a use on another motherboard in the future. You see many motherboards have prediction with these pins here on the CPU side. So okay, here I have another 386 motherboard. It is the same chipset, just a later revision and a later version here of the PCB, but it looks very similar. However, here I had a lot of battery damage and this is partially working. I have already spent a lot of time here, but yeah, this needs more. Then the bad thing is that here you can see also the prediction for these pins, but the layout is a bit different. So okay, I will have to make a different version of this one. However, most motherboards actually have this configuration I have made already. So you will definitely see all this again in the future. One other thing I forgot to mention is that the floating point units worked just fine. Okay, the first one had some problems, but then I tried another brand and worked okay at 40 MHz. Now on this topic I have many 487SX chips, and also we can play here with asynchronous mode. So all this of course it's a topic for another video. It's very interesting to see all this interaction. So I think that all this concludes this video. I'm not totally happy here, but okay, I had a lot of fun. I hope you also liked this one. Feel free to give me any feedback you like and subscribe for more like that. So that is for today, and yeah, see you again next time.